Hey, welcome back. Today we're going to take a look at applications of the partial derivative. Now, a lot of this will seem very familiar to what we did last year in calculus. So let's say, suppose we want to find and determine whether a function is increasing or decreasing. Now, from last year, we said that this is a rate of change, and of course, these things just rock. We can accomplish this by finding partial derivatives. So let's say we have the function f of xy is given by this y squared divided by x cubed. We want to determine if the function is increasing or decreasing at the point 2,5. Now, if you're not really good at derivatives, give me a second here. So if you can't remember your little shortcut for derivatives, we can just write this as y squared x to the negative 3, and it might help to take the derivatives. So our first partial derivative, let's just take the partial with respect to x. So since I wrote it up here, it's just our power rule. This is just drop your power. We're going to get this negative 3 y squared. Remember, this becomes x to the negative 4, and I can just write that as x to the 4th on bottom. And I can plug in. Therefore, my partial at the point 2,5 is just going to be negative 3 times y squared, which is 25, divided by 2 to the 4th, which is, of course, 16. Now, I don't know what this is, but we're only asking if this is increasing or decreasing. And since this is a derivative which finds slope in the x direction, I already know that that's less than 0. Therefore, I can say that the function f of xy at the point 2,5 is decreasing in the x direction. And likewise, I could do the same thing for the partial with respect to y. So when I take the derivative with respect to y, we are going to get 2y over x cubed. And again, if I find the partial of y at the point 2,5, I'm just going to plug that in. 2 times 5, of course, is 10 over 2 cubed, which is me. I'm just way 2 cubed. Just kidding, it's 8. And this time, we get something greater than 0. So because the slope is greater than 0 from last year, we know that this is going to be increasing. Therefore, the function f of xy at the point 2,5 is increasing in the y direction. So we have a particle, or whatever, decreasing in the one direction, but increasing in the y direction. It seems kind of hard, but it's kind of like, I always kind of like imagine climbing like a hill or something like that, where we have multiple directions. We'll talk more about that a little bit later on. All right, so let's take a look at an application. So imagine you are on a sailboat in the Bahamas. So let's imagine we're on a sailboat in the Bahamas. Suddenly a storm comes in. The wind generated by the storm at a point on the ocean is given by this equation. W of xy, sounds like it's a radio station, 0.015 x cubed y to the 4th. As captain of the boat, you need to move the boat out of harm's way. However, due to hitting a rock, that should be due. If spell check never catches my spelling, please don't ever expect me to. Due to hitting a rock, you can only move in either the x or y direction. What direction should we move when we're at the point 3,2 so that we move in the safest direction? So we're looking at the rate. So if this right here is the storm, the wind, we want to know about how that rate of the wind is changing. So we have to find the partial. So the first partial we're going to find is the partial in the x direction. And if I take the derivative, in terms of x, this becomes 0.045 x squared y to the 4th. And if I find that partial at the point 3,2 where we're located, again, this could be like latitude, longitude coordinates. We can find out what the change in the wind is at that point. I'm going to use my calculator for this. Okay, so let's see here. Calculate, and I'm just going to plug that in. This becomes 0.045 x squared. Well, x squared, which x is just going to become 9 times, we should put that so we're not confused, it's a decimal, 2 to the 4th, which is 16. And I can just plug this in. So let's see what happens when we plug this in. Oh no, my thing went kind of haywire there. There we go. So I go 0.045 times 9 times 16. Now I don't have any units here, so it's just going to be 6 point. So we get this 6.48. So remember, this is representing the change in the wind in that direction, in the x direction. I do the same thing for y, the partial with respect to y. Let me see here, 0.4 times 0.4 times 15. Oh no, Mr. Warner, I messed up. 0.015 times 4. I see what that is. Oh, that's just 0.06. I always 0.06. We're going to get x cubed, but this becomes y cubed. And we find the partial of the wind with respect to y in the y direction at that 0.32. And we just plug it in, 0.06. This becomes 3 cubed, which is 27, times 2 cubed, which is 8. And we just type all that in our calculator. 0.06 times 27 times 8, and we get 12.96. Now remember, this is the change in the y direction right here. And so we're looking for the safest direction. Well, if you're looking for the safest direction, you're probably looking for the part where it changes the least. So it looks like we're going to head in the x direction. So we would head in the x direction because it changes the least. Probably means it'll be safest for us. All right, so kind of a neat little application for us. All right, so let's take a look at this in the business world, okay? So let's say the value of an investment, so the value, so they're giving us a value function here of $1,000 earning 10% compounded annually is given by this formula. V is a function of I and R, where I is the annual rate of inflation and R is the tax rate for a person making the investment. Calculate VI, the partial with respect to I, where the inflation rate is 3% and the tax rate is 28%. Oh, those darn Republicans, or Democrats, whoever wants to tax us this time. All right. So, and then we want to find the partial of R also at the same point when the inflation rate is 3% and the tax rate is 28%. So we want to calculate those tax rates. So for the first one, now this is pretty ugly to work with, so I am going to kind of break it down. I notice the top part deals with the tax rate, the bottom deals with the inflation rate. So I'm going to separate those two and make this 1,000, 1 plus 0.1, 1 minus R to the 10th, divided by, so I'm just going to separate the fraction, 1 plus I to the 10th right there. That's going to make my derivative maybe a little bit easier for us. All right, so let's go and find the partial with respect to I. If we do this with respect to I, we're looking at the bottom. The top is a constant. So if I think about this, this is kind of like saying 1 over I to the 10th, which is just I to the negative 10. And that derivative is easy. We're going to get negative 10 I to the negative 11. So I know the bottom is just going to be this 1 plus I to the 11. But the top, I'm going to multiply it by negative 10. And that becomes a negative 10,000. And everything else stays the same. 1 plus 0.1, 1 minus R to the 10th. And I can just plug in my values at 0.03, 0.28. And when we do this, we would get negative 10,000, 1 plus 0.1 times, this becomes just 0.28 to the 10th over 1 plus 0.03 to the 11th. And I already went ahead and did this for you. What we wind up with is negative 14,478. Now we don't have any units to establish right here, but we'll talk more about application like in units later on. So we get this negative 14,478. So right now it's just a number. We'll talk about what it means in just a minute. But now we want to do the same thing, but this time with the partial with respect to the rate, interest rate, or tax rate, sorry. And if I take the derivative here, the bottom is a constant. That's just going to stay the same. So that's just going to become 1 plus I to the 10th on the bottom. But when I take the derivative of the top, that becomes 10,000. It's a chain rule. 10,000 times the inside stays the same, 1. Now, what I might do to help me out a little bit here is distribute this. If I distribute the 0.1, I'm left with 1.1 minus 0.1 r. And that's going to help me take the derivative. So the inside is just going to be this 1.1 minus 0.1 r, I should say 0.1 r there, to the 9th, but now I take the derivative of the inside, I get this negative 0.1 right there. There's a 1 there. Sorry about that. There we go. All right. So now when I find the partial at our point, 0.03, comma 0.28, we're going to get, plug everything, if I multiply this out, this becomes negative 10,000, 1.1 minus 0.1 times, what's r? 0.28 to the times negative 0.1 over 1 plus 0.03 to the 10th. And I already simplified this out for you. You get negative 1,391.17. So this is the effect that just the tax rate will have on it at that point. And this is the effect that the inflation rate will have on our investment at that point. So determine whether the tax rate or the inflation rate has a greater negative factor on the growth of our investment. Well, that's pretty obvious. It looks like inflation has a much greater negative factor. So it's just telling us the taxation rate only affects us by about 1,400, but the inflation rate really affects our investment. That's why we have what's called cost of living. We always got to adjust for the inflation when it comes to prices and even paying people. So inflation rate does have a very big negative factor on the growth of an investment. So we would say, of course, the inflation has the greater negative impact. And all right, so I hope you enjoyed this video. Go to part 2. We'll take a look at some more examples. I'll see you then. Bye-bye.